Welcome to this physics lesson about pendulums. Today, we're going to understand two important types of pendulums, the simple pendulum and the physical pendulum. Let's start with the simple pendulum. A simple pendulum consists of a point mass suspended from a fixed point by a massless, inextensible string. The mass is concentrated at a single point at the end of the string, and the string itself has no mass, meaning all of the mass is concentrated at the bob. When released from rest, the pendulum swings back and forth in a regular motion. For small angles, this motion is approximately simple harmonic motion. Let's look at the forces acting on the pendulum. The weight of the bob acts downward with a magnitude of mg. The tension in the string acts along the string towards the pivot. We can break down the weight into two components: mg cosine theta, which is balanced by the tension, and mg sine theta, which provides the restoring force tangent to the arc of motion. For small angles, the restoring force is approximately proportional to the displacement. This leads to simple harmonic motion, which gives us these important equations. The angular frequency omega equals the square root of g over L, where g is the acceleration due to gravity and L is the length of the pendulum. The frequency f equals omega divided by 2 pi, which gives us 1 over 2 pi times the square root of g over L. Frequency tells us how many oscillations occur per second. The period t is the time for one complete oscillation, which equals 2 pi divided by omega, or 1 over f. This gives us 2 pi times the square root of L over g. Note that these equations depend only on the length L and gravity g, not on the mass or amplitude for small angles. Let's calculate the period of a simple pendulum with a length of 2 meters. Given length L equals 2 meters, acceleration due to gravity g equals 9.81 meters per second squared using the period formula, t equals 2 pi times the square root of L over g. We get t equals 2 pi times the square root of 2 divided by 9.81. Computing this, we get a period of approximately 2.84 seconds. This means a complete back and forth swing takes 2.84 seconds. Now, let's move on to the physical pendulum. Unlike the simple pendulum, a physical pendulum is any rigid body suspended from a pivot point, free to swing back and forth. It doesn't need to be a point mass. Examples of physical pendulums include a swinging door, a clock pendulum with distributed mass, or any irregular object hung from a point. The motion of a physical pendulum is also simple harmonic for small oscillations, but the equations are a bit different. The angular frequency omega equals the square root of mgd over I, where m is the mass of the object, g is the acceleration due to gravity, d is the distance from the pivot to the center of mass, and I is the moment of inertia about the pivot. The period t equals 2 pi times the square root of I over mgd. Unlike the simple pendulum, the period depends on the mass distribution, moment of inertia, and the distance from the pivot to the center of mass. Let's compare the simple and physical pendulums side by side. On the left, we have our simple pendulum with all mass concentrated at a point. On the right, we have a physical pendulum with mass distributed throughout the object. For a simple pendulum, the period depends only on length and gravity. For a physical pendulum, the period depends on the mass, gravity, distance to center of mass, and moment of inertia. An interesting relationship is that any physical pendulum behaves like a simple pendulum of a certain equivalent length. This equivalent length is I over md. In fact, if we make the distance d from the pivot to the center of mass very small, the physical pendulum will oscillate more slowly, meaning it has a longer period. Let's look at some real-world applications of pendulums. Pendulum clocks utilize the consistent period of a pendulum for timekeeping. Seismometers use pendulums to detect and measure earthquakes. The Foucault pendulum demonstrates the Earth's rotation. And of course, playground swings are essentially pendulums with you as the mass. Let's summarize what we've learned. For a simple pendulum, the period t equals 2 pi times the square root of L over g. The period depends only on length and gravity, not on mass or amplitude for small angles. For a physical pendulum, the period t equals 2 pi times the square root of I over mgd. Here, the period depends on the moment of inertia, mass, distance to center of mass, and gravity. Understanding pendulums helps us grasp many important concepts in physics, from simple harmonic motion to conservation of energy. Thank you for watching.